Just the day before, Greenville was still a peaceful little American town of 1,000 inhabitants. On August 4th, 2021, it looked like this. It only took 30 minutes for the flames of the Dixie Fire to devastate 75% of its buildings. And if no one perished that day, it's because megafires are becoming commonplace in California. And everyone knows there's not a minute to lose. These enormous fires leave little room for hope of returning to normal life. They may represent only 3% of the fires on the planet, but are the cause of more than half of all burned surface areas. These fires are capable of engulfing more than 12,000 acres of forest per hour in flames. The term megafire is not a haphazard term. It describes a new phenomenon unique in its size, unprecedented in its behavior, and unprecedented in its consequences. A new fire war is beginning for scientists against a phenomenon whose secrets researchers are just beginning to unlock.
To make progress in the science of wildland fire, what we have to do is forget all of the things we think we know.
We're realizing that the intensity and the aggressiveness of these fires continues to grow, but to reach what limits, we don't know yet. Because every year, the intensity of these fires grows more and more.
From one region of the globe to another, megafires are never identical, but their danger now hovers over all types of ecosystems. To defeat a fire, you must be able to identify it, but the mystery is as complex as the adversary is varied. This film exposes a new challenge: to dismantle the mechanics of a phenomenon that is rapidly overtaking the world. In California, the Dixie Fire continued its course for 3 months and burned almost 1 million acres. The previous year had been the Glass Fire or the Bobcat Fire. Here, these fires are so numerous that they are named after the places where they first broke out. According to the California authorities, over the past 20 years, the fire season has lengthened by 75 days, now extending from June to September, whereas it only lasted one short month in the past.
As it currently stands, we have over 2,000 firefighters, as you can see here, and our big concern right now is a changing weather pattern over the next 24 hours. That includes red flag warnings and extreme heat conditions.
In this new one-sided fight, the fire hose is no longer enough. It's in a trailer a few miles from the flames that the California Fire Department sizes up its weapons. For 6 years now, for each fire of almost 1,500 acres, the authorities have called on 2 experts on fire behavior and weather. 2,000 firefighters await their predictions on the evolution of the current fire.
Yeah, looking at the map from last night, it looks like most of our activity is up on this kind of north and west section up here. So, I expect today we're going to see a lot of the similar type of activity up there.
Yeah, and the good thing with the light winds, there's not going to be a strong push against any of these hot lines right there, so it won't try to make it run too fast today. But tomorrow, with the increasing winds coming from a new direction, there's going to be a lot of push on the fire from the northwest towards the southeast.
Yep. So we'll take
So we're ramping up in all regards as far as fire weather concerns are considered: hotter, drier, and windier, with a new direction on the fire that hasn't seen yet.
In California, dry soil conditions have increased by 20% in 50 years. In the west of the United States, fires have always been part of the natural cycle of forests. But in the past, the fire season had an end, and firefighters knew how to handle their enemy.
a 40,000 acre fire, when I was a much younger firefighter, was a very large fire. And now 40,000 acres is a single day on some of our large fires. In California, as it stands, I think we've had maybe half a dozen of those this year so far. So that's very unusual, and it's a definite change.
The fire that we were on previously 10 days ago was 900,000 acres, almost 1 million acres now. That would be, to me, a megafire. That's not common, that's not normal, but unfortunately it's becoming more normal.
When California is suffocating, all of America has trouble breathing. More than 1,000 miles away, the Rocky Mountains in the north of the country fade away. And the smoke from California deprives Montana inhabitants of the sun. It's here in Missoula that scientists are trying to unlock the secret of how fire behaves. This study laboratory, unique in the world, was created 50 years ago. Mark Finney and his team study the physical principles of forest fires.
C2292, 1.4 meters per second, 150 SLPM, one burner, 0 degrees.
Should we rotate or go with 225?
I have some ideas.
Yeah.
This new phenomenon of megafires is still poorly understood by researchers. But they are now sure of one thing: a fire almost 2,500 miles wide doesn't behave like a conventional fire.
There are many different ways to describe fire, or different types of fire that one can see, right? Often they're classified by the fuels that they're burning in. They may be burning in the litter or the surface fuels versus in the crowns of trees, and those would be crown fires versus surface fires. But another classification that we often rely upon is a distinction between what we call a line fire and an area fire. Say you have fuel conditions that burn for a very long time. Deep duff and litter layers, large concentrations of woody fuels on the ground. And what happens is this flame zone still spreads very quickly, but it continues to burn and continues to burn. And on the extreme end of that, a term that's been used recently is megafires.
In a classic fire, the flame front advances like a line in the forest. A curtain higher than the trees, which sweeps across the forest. As it progresses, it leaves behind a charred area. Conversely, in a surface fire, the flame front still advances, but the area behind the flame front continues to burn on the ground constantly.
Here we go. Now the differences in fire behavior from the two are pretty dramatic. In a line fire, the oncoming wind usually penetrates the fire front. It blows through it in little channels, okay? And so we see, if you look at the shape of a line fire, you see these peaks and troughs in the flames. In the low part of the flames, the wind is able to penetrate and get through. And in an area fire, if you have a very, very deep flame zone, what happens is the air cannot penetrate through the fire anymore. The strong buoyancy, the strong updrafts from all of this heat generated over a large area basically obstructs the passage of the wind, and it has to flow around the fire. And so it changes completely what's going on inside the fire. And this material is about 1 millimeter?
Yes, so it's a very fine material, but it is very densely packed, much like the duff layer on the forest floor.
One of the questions that perplexes the laboratory teams is why, above a certain size, a forest fire seems to grow by itself, as if it was feeding on its own energy.
But if we put it under the chimney, so in this experiment, we simulate a large fire, right? So when the fire gets really, really big, the plume above it gets really, really wide, and it can't entrain a lot of air. So if it can't pull in cold air, the plume gets super tall, like into the stratosphere, like we see in some of these big fires. We think that this is one of the things that's happening with those big megafires. They get really big, they start blocking off the airflow into the plume. It generates its own fire wind, which then fans the flames underneath it. And so this is what we do with this chimney, is to simulate that behavior, is we physically block the air with the chimney to understand how it changes the burning behavior of the fuel underneath it.
Do you have any idea how many times faster it burns with the chimney than if there was no chimney?
Where it can burn like 3 times more, 3 times faster than without the chimney.
The Megafire therefore behaves like a huge chimney fire, a chimney that draws too efficiently. In a forest fire, this natural chimney is called the convective column and is made up of hot air, gases, and rising smoke. Nature hates a vacuum. If hot air rises, something has to replace it. Cold air. But the bigger the fire, the less this column of hot gases mixes with the cold ambient air. This creates a huge draft at the base. Winds induced by the fire itself, which in turn rekindle the fire. During the North American and Australian megafires, the convective columns were incredibly big, sometimes more than 6 miles high. They generated what are called pyrocumulonimbus clouds. Immense clouds saturated with humidity, which, upon meeting a dry atmosphere, generated thunderstorms and lightning. These same flashes, which, in turn, generated new fires, sometimes miles from the main front. The perfect vicious circle.
Yeah, spot fires galore down here. We're talking about 60, 70 metre flame height. 60, 70 metre flame height.
It was precisely these convective fires that ravaged Australia in 2020. That summer, the bushfire season was among the most violent in the country's history. Almost 45 million acres went up in smoke. Black Summer. This is the name that the Australians attributed to this exceptional period, which lasted nearly 9 months. Greg Hardy experienced these megafires on a human scale. He was able to observe the dynamics of these new phenomena from the inside. Captain of the Dunmore Fire Brigade in New South Wales, he led 3 months of war against the biggest fires in the world. On January 4th, 2020, his truck's onboard camera remained in the heart of the furnace as everyone else moved out of harm's way. The video reveals, from the inside, the energy released by these new types of fires.
We thought that we still had a good 10 minutes on the clock. So the guys were just relaxing, getting some water from a local crew, and then that's when things hit earlier than expected. It was kind of calm. We could see where the fire was. It was probably about 100 metres or so into the bush, and flame height was probably only about 1 metre high. But when it changes from that height and that wind speed of 5 k's an hour to 105 in a matter of 2.5 minutes, that was what was a massive eye-opener for us. You could hear it coming. It was like a freight train when that wind was coming through. And to see it from your own eyes, of going from basically 2 metre flame height to over 50 metres and went straight over our truck, massive eye-opener for me.
These flames of unprecedented proportions even managed to devastate the Blue Mountains National Park. which is made up of less arid vegetation than the Australian bush. Barely 2 hours from Sydney, this nature reserve, which is home to a plant diversity unique in the world, has seen more than 20% of its surface area devoured by the flames. Professor Ross Bradstock is one of the foremost specialists on the ecology of fire. 2020 was the first time in his career that he had seen all climatic conditions converge to create these megafires.
You can see that the whole base of the tree has been hollowed out by successive fires. In itself, that tells a story. It tells you that fire is a regular occurrence in this landscape. One of the reasons why it got so large was because the landscape was homogeneously dry because of the record drought. So normally the natural barriers to fire spread, which are creeks and canyons, they were dry because of the drought. The fire was able to get across those, but also the unrelenting weather conditions. Virtually every week while this fire progressed, we had a day of really severe weather where the wind and the temperatures and the humidity produce extreme fire behaviour.
Drought and climate change are two decisive ingredients for the spread of a fire. The third is the very material of this forest, eucalyptus. This cocktail is enough to start fires that were never before seen in these temperate forests of southern Australia.
We're looking at the fundamental element for fire, which is what we call the surface litter fuel in a forest. And we can see in these eucalypt forests that it's composed of primarily of the leaf and twig material that has fallen down from up above and the tree crowns. We can see how the leaves are arranged in the litter. They pack very loosely, which allows plenty of gaps, which is a sort of ideal arrangement in terms of creating a nice flammable fuel layer. So here we'd probably have about 1.5 kilograms in a metre square of fuel.
The flammability specific to the eucalyptus is not only linked to its leaves, it is also due to the structure of its bark.
This suspended bark material creates essentially an above ground vertical layer of fuel, which potentially can aid the transmission of the flames from the surface litter up into the shrubs and then under certain weather conditions even into the canopy of the trees. There's a potential for these pieces of bark, to go up that high and then get moved by wind many kilometres ahead of the fire.
A very recent study reveals that the area burned in Australia has increased by 800% on average over the past 20 years. The flammability of Australian forests is now a chronic threat. There's another forest, on the other hand, which in principle should never have caught fire. It's the Amazon. With a humidity rate of more than 80%, fire is even unnatural. No question of burning standing trees. They are too waterlogged. So to create pastures or produce soybeans, Amazonian farmers have developed a radical technique. Cut down the trees with a bulldozer, dry the trunks in the sun, and then set them on fire. Erica Berenger is a Brazilian researcher who is fighting for the preservation of this forest. But since 2 years, she has not been able to set foot in the Amazon because of the COVID crisis. In the meantime, she consoles herself with tropical plants from European greenhouses and continues her study of deforestation by fire from afar.
One really big problem of those deforestation fires is that they can escape the area that they were designated to burn and invade surrounding forests, so forests that are around the area that is being deforested. And once they get into the forest, because it's a rainforest, it's super humid, the fire should die out. But the problem is we have climate change, so the forests have become drier and hotter. And one thing that is crucial to understand is that these fires are very different from the fires that we see in California, for example. They are about 30 centimeters. They're very small. And I put so many fires out just with my boots. That scale fire can be extremely harmful to the forest, killing half of the trees. And when I say half of the trees, I mean half of the trees that are above this size. The trees that are below the size, so trees like these that are around us, 90% of them die. 90% of them die.
These small fires, creeping under the canopy, escape satellite observation, but they detect the big fires started by the farmers. The red dots in this photo, taken on August 9, 2021 in Brazil, represent all detected thermal anomalies. Satellite imagery bears witness to the constant progression of clearing by fire in the Amazon over the past 20 years.
That's very problematic because, one, biodiversity is very different in those forests. So we have a change on the species of both the fauna and the flora, but also we have a change on the amount of carbon that the forest stores. The forest loses a lot of carbon when it burns. And that's because if you think about a big Amazonian tree, those that we see in documentaries that are beautiful, they store about 20 tons of carbon. Half of the weight of a tree is carbon. 30 years after a forest burn, it stored 25% less carbon than a forest that never burned. This means that in 30 years, a forest does not recover in terms of carbon stocks. And we just don't know if ever those forests will ever recover that amount of carbon that was lost, or if it's just gonna take centuries. We just don't know. We haven't been studying long enough.
It is estimated that the Amazon rainforest counts 10 billion trees, a free carbon storage service for humanity, ready to go up in smoke. In Amazonia, Australia, or North America, by definition, a megafire flourishes on immense forest spaces. But in Europe and in the Mediterranean basin, a change is nevertheless taking place. In the summer of 2021, the region experienced up to 12 times more burned surface area than the summer average. More fires, of course, but which many are still reluctant to call megafires. One man, however, believes that the threat in Europe has already emerged. He launched an alert in 2016, sometimes with the impression of shouting in the desert. Eric Rigolo is a researcher in the ecology and physics of fire. He insisted on taking us to Rognac, at the gates of Marseille, where the training of water bombers hasn't stopped for 40 years. Where above all, according to him, the first episode of Megafire, à la Française, occurred.
Here the fires started at the house in the distance, below the cliff. It was under construction, and very quickly the fire rose in power into the trees, skirting the cliff, and began to jump the cliff.
Nothing to do with the scale of the Australian megafires. And yet, on August 10, 2016, the uncontrollable nature of the fire near the second largest city of France marks a turning point in the history of French forest fires. 2,000 constructions are threatened by its trajectory, and hundreds of motorists find themselves trapped.
We know from experience that fires in this zone are extremely difficult to control. We are next to Marseille and many towns. A fire starting in these conditions will be an extreme fire. This fire began at 3 p.m. and arrived at 11 p.m. at the end of its path, so in 8 hours, it covered a distance of 9 miles, with accelerations which were measured at up to 3 to 3.5 miles per hour on the plateau. These are record speeds recorded on this fire.
By way of comparison, a conventional fire only advances at a little more than half a mile per hour. That day, the unprecedented speed of fire spread was fueled by the wind and by what are called fire jumps in front of the flame front. The jump is the Megafire's perfect ally.
A fire jump is the projection of a glowing particle starting from the main flame front, which jumps over unburned vegetation to create a new fire far ahead of the flame front. In the past, it was thought that these fire jumps were the result of malicious arsonists who were sending the firefighters around the forest fire. In reality, it is the fire itself that generates these new fires, and it accelerates the spread of the fire enormously.
Fed by these fire jumps of sometimes more than 1,000 yards from the focal point, the Rognac fire consumed almost 500 acres of forest per hour and spread as quickly on its flanks as in its length. This is the first time that such a scenario occurred in France.
Sooner or later, with climate change and extreme seasons that are multiplying, heat waves and drought, this type of fire will multiply, and we must be prepared for that.
These types of exceptional episodes presage what scientists today call a change in the fire regime. In other words, a change in seasonality, frequency, extent, intensity, and behavior. It is these erratic behaviors that scientists are struggling not only to understand, but also study.
Even though there's a lot of unknown factors associated with even predicting line fire behavior, all of those unknowns are dwarfed by comparison to the unknowns associated with an area fire or some of these very large fire behaviors. One of the reasons that those remain even more unknown is that they're hard to study. Right? You kind of have to study those large fires in the context of those large fires. So it's very difficult to do experimental work on large fires. So our challenge here in the laboratory is to take certain processes that we know are occurring in those large fires and examine them at some smaller scales and understand them at scales where we can control those processes. See, it's still spinning on down, just spins right up. You know, you have that, usually you have that confused, well, kind of like this.
One of the mechanisms that the Fire Science Laboratory produces on a smaller scale is the fire whirlwind. This phenomenon has always existed, but the new proportion of fires has changed the situation. With a megafire, we now speak of a fire tornado. Some can reach almost 1,500 feet in diameter.
What this is, and this can happen out in the real world in a forest fire. So when you get some swirling air, slow swirling air over a large area, if you have a fire there burning, what the fire basically does is that buoyancy and the sucking from the fire, that air that's entraining into the fire, can bring that swirling air and concentrate it into a smaller diameter. And what it's doing is taking this swirling air and stretching it vertically. The accelerating plume of the fire stretches it. As you reduce the diameter, the fire spins faster, the rotation spins faster. Fires that have this rotation have this special effect that they contain their energy, both the rotating energy and the temperature of the flames and the gas. if there's a wind blowing, sometimes that fire whirl will move with the wind and detach or separate from the fire and can contain its energy without any heat source anymore, which is where a lot of the original energy for the spinning comes from, and be blown downwind quite a distance and stay spinning for a long time. We've documented some that can burn up to an hour, spin up to an hour. The only thing to do is get out of the way.
On some fires, the rotation speed of these tornadoes have been estimated at almost 125 miles per hour. Firefighters are used to saying that you should never try to fight them. This is also one of the definitions that scientists give megafires today, fires that lead to the firefighters' loss of control. This is precisely what almost happened in Sweden in 2018. Swedish firefighters found themselves overwhelmed by a situation for which no one in these latitudes was prepared. Abnormally high temperatures simultaneously initiated more than 44 fires in the boreal forests, as far as Lapland and above the polar circle. Europe will warm faster than the rest of the world. So says the latest IPCC climate report. But near the Arctic Circle, some estimate climate change is already 3 times faster.
This is my favorite tool. I can't get by without a magnifying glass.
Jean-Michel Roberge is a specialist in biodiversity conservation. For 21 years, the Canadian has been tracking endangered species in the middle of exploited forests in Sweden. Mushrooms, mosses, which in particular, under the effect of climate change, are moving north. The boreal forest is one of the largest ecosystems on the planet. Scandinavia, Russia, Canada, Alaska. It represents 30% of all of the world's forests.
What are characteristics of the boreal forest? First, it is a rigorous climate. We have very cold winters, a good amount of snow, and freezing that gradually penetrates the ground. We see here that the ditches are waterlogged. Despite appearances, boreal forests are vulnerable to forest fires in the same way that many other forests are on the planet. Due to climate change, we can expect an even higher risk of fire in the boreal forests. Here in Sweden in particular, there are some climate models that predict summer droughts will be even longer in the summer, and this could lead to higher fire risks as well.
Whether it is forests of Swedish conifers, German firs, or Land's pines throughout Europe, fire can now count on an unexpected ally. An ally just a few millimeters large.
Here we have bark beetles. It's an insect that belongs to the beetle order and that reproduces under the bark of spruce trees. It's a very small insect that doesn't look too dangerous, but when they arrive by tens of thousands, they can kill a tree quite easily. Here we see a bark beetle that was born this summer, and another one here.
By digging galleries in the cambium, a thin layer under the bark, females block circulation of the sap to deposit their eggs there. The tree dies in less than 4 weeks.
The female lays her eggs in the main gallery, and the larvae disperse on each side of the main gallery.
This insect, whose size varies between 2 and 7 millimeters, is naturally present in our ecosystem. But extreme climatic conditions favor its proliferation in softwood forests.
With higher temperatures, it's possible to have two generations that develop within a summer, and this could increase the damage, almost double the damage on the forest.
In some parts of Europe, there is even talk of an epidemic of the bark beetle. Why is this insect the perfect accomplice for fire? Because, by condemning trees by the thousands, it promotes the accumulation of dead wood in the forests, an additional risk for outbreaks of megafires. How frequent will these large fires be? This is the question that plagues scientists around the world, and it may be engineers who hold the answer. At the National Institute for Agronomic and Ecological Research, François Pimont develops fire prediction models, increasingly precise tools on which firefighters hope to rely in the future.
In our unit, we work on the behavior of an individual fire, how it will spread over a small landscape depending on different factors. And we also work on fire activities, or how on the scale of a large landscape, a region or a territory, we will have a certain number of fires that will start, spread, and lead to a burnt surface. In the two simulations above, we represent the behavior of the fire corresponding to a situation of moderate hydric stress at the end of springtime, to a situation of advanced hydraulic stress corresponding to the middle of August. In this case, we see that the fire spreads essentially in the shrub layer, with some cases where it will burn in trees. Some are not burned, and the fire spreads much more slowly than in this case, the only difference being the dryness of the vegetation. In this simulation here, it is the same configuration with an intermediate hydraulic situation, but this time there's a strong wind. We see that the flames are much more elongated, with a very flattened plume, and a fire that burns all the trees in its path. What we see on these simulations is that these parameters, the hydric and wind and the slopes, are very important, because these three fires had the time to propagate, while this one had just the time to go from the beginning to the end of the domain. These models are also developed to be able to understand how we can affect the behavior of the fire by treating the vegetation. Because among the factors that affect the behavior of the fire, we've seen that there are meteorological factors, topographic factors, slope, and then the vegetation. The only one on which humans can concretely act apart from our emissions on the climate is the vegetation. By suppressing the vegetation, we reduce the quantity of material susceptible to burn, so naturally the power of the fire.
But the pride of the INRAE team is their brand new model, which makes it possible to evaluate the probability that a fire exceeds 2.5 acres. When a fire exceeds this surface, it is said to escape and threaten to turn into a megafire.
Escape fires are very important because they require massive interventions of the fire departments, since these fires could not be contained with a limited intervention, and thus imply a significant deployment of firefighting forces. Being able to provide a fairly accurate indication of the number of interventions that will occur allows firefighters to organize themselves, especially since fire seasons tend to be longer, and therefore managing the periods when there is less fire allows savings in order to be ready when it is necessary to deploy maximum forces.
This brand new prediction tool is attracting the interest of the French Meteorological Agency and the French National Forestry Office, because at a time when the fire season never ceases to expand, knowing when to prepare for the worst could help firefighters become more efficient. Faced with this threat, all specialists agree on at least one point. Increasing the number of firefighters is no longer enough. To counter fire, you have to call on fire.
The objective today is to create a burn to decrease the intensity of the flame's front. As you know, the plateau of Arbois has been regularly crossed by the fires. We see very little forest around us. It's occurring regularly, about every 10 years in 2016 and 2004. The objective today is not to stop the fires. We know the plateau won't stop them. We want to diminish its intensity before it arrives here.
The Vitrolles mountain range of the Bouches-du-Rhône region is a kind of corridor where the Mistral wind rushes in every summer, and fire often along with it. To prevent these summer fires, firefighters are preparing to carry out a combustible cut, a fire lit voluntarily and under control in the middle of winter on the established course of fires. These strips of burnt land will prevent big fires from continuing their course when the summer comes.
Start ignition of the site. Start ignition. Come on, guys. We're in control of things. It's all good. This fire won't degenerate. Don't be afraid.
Burning is practiced against the wind and in backing away. The fire is lit on a slope in successive lines. Each line of fire progresses slowly up the slope before being stopped by the previous charred zone. 17 acres must be consumed, not one more. It takes wind for the fire to catch, but not too much, to prevent it from escaping. For here, the wind can pick up in just a few minutes.
You see, the flames are a little higher now than before.
12 firefighters are in charge of lighting them. 18 others are ready to put out the flames that escape. Vincent Pastor is the orchestrator of this specialized team, both firefighter, forester, and contained burning instructor. Science requires a perfect knowledge of fire behavior.
The pressure! Stop, stop, stop! Come on! You got it! You got it! It's okay, it's all cleared. When we conduct a burn, we're attentive to its behavior. The behavior of the fire will drive our actions. We will first listen to it. The closer the crackling sounds are, the stronger the fire's intensity. The more regular the crackling is, on the same tone, indicates a regular, very low flow. So we listen to that. The fire must continuously make the same noise. Its noise must not decrease, or we will lack efficiency. Its noise must not increase too much, otherwise it will be too powerful. So it's necessary to manage it, or rather to conduct this music throughout the fire. We will then observe the smoke. What color is the smoke? Is it white? That means that there's a lot of water in the plants, in which case we have to develop a little more intensity to remove this water vapor to burn the plants. Is it brown? A sign of pyrolysis. That's the chemical composition of the plants under the effect of the heat. That's a sign for prudence, because we can have a music that accelerates. We don't want that. And so someone must manage our ignitions, and we will keep an eye on the smoke. We'll watch, listen to the noise. We'll watch the flame. What color is it? When it's reddish, it is from a combustible vegetation. When it's orange, it propagates less because it's in plants with a higher water content.
Controlled burning has long been neglected in France for lack of practitioners. It is still highly regulated. Fire as a fire prevention tool has not always had a good reputation. Contrary to popular belief, controlled burning does not destroy the structure of the soil and is only practiced in winter when the fauna and flora are dormant.
If I pick up some ground, I notice that the temperature is cool. The ashes are already cool. And if I scratch a little more, I find all the little roots are cool. They've not been impacted by the fire. We touch and we feel the moisture. So in fact, we had no impact on the soil. The fire passed quickly. And thanks to that, we have no impact on the vegetation. We only destroyed the vegetal apparatus. The lower part, the seeds, the mycelium, is still humid. Here's a root that is not burned, that is supple, because of the speed of the fire, its intensity, and the fact that it's winter, and that the fire has passed quickly with a power controlled by the igniters.
The temperature at ground level will only have increased by 1 degree and 3 centimeters. With a large fire, on the other hand, all traces of life on the ground would have been destroyed.
It's going to get hot up there.
Vincent Pastor is now training controlled burning teams throughout Europe, convinced that this prevention tool is still not widely enough used. In his eyes, however, it is one of the best responses to megafires. In the Aboriginal lands of northern Australia, fire was used as a tool for 65,000 years before becoming an enemy. Arnhem Land is extremely inaccessible to the outside world. An Aboriginal reserve since 1931, it is known for its isolation and the attachment of its inhabitants to their traditions. This is arguably why the area is one of the few in Australia to have maintained its traditional burning practices. It is not a question of creating a firewall zone, as French firefighters do. It is rather a question of cleaning the bush just after the rainy season. By setting fires of very low intensity to maintain the balance of the forest and avoid any outbreak of large fires.
They can't wait to light them. And they're not scared because him always come with me, and I'm learning him and Levi, already doing it. And sometimes I'm a bit worried because they don't worry about all that flame, but sometimes I'm worried. Him just like wild cattle, you know. You have to talk to him, or horse. You have to talk until the owner of the horse, they get used to. When him do finger signal, that horse him come. Him tell him turn around, him turn around.
The Aboriginal populations of Arnhem were driven out of these lands by the settlers, and today live mainly in the cities. But better than anyone, they know the fragility of their territory in the face of the risk of major fires. Dean Yerbarbuk is one of the representatives of Arnhem Land, a renowned chief who has long campaigned for the prevention against megafires to be entrusted more to Aboriginal know-how.
Well, our people in the northern area, in the northern territory, along the northern coast up here, people has been practicing for thousands of years. And, well, you know, after the colonizers happened, everyone got restricted off. And cultural burning, in Arnhem Land here, we have been practicing for thousands of years. When we trimmed our native floras and faunas down, rather than having, living unmanaged or unburnt area, just like in the southern area, where one day someone would come around and throw matches. It's unstoppable. If the indigenous people across another state within Australia, if they would have done this similarity like what we have been doing for 100 years ago, all Australians would have been nice place to live, and no wildfires would have existed.
In 2006, Dean Yerbarbuk launched an initiative that few people in his community believed in. The first ever Aboriginal carbon credit scheme. By practicing traditional burning, the rangers protect the territory from the risk of megafires and earn carbon credits for their people. In Arnhem Land, this regular practice has reduced CO2 emissions by 882,000 tons per year.
We know there's a lot of government there waiting and talking a lot of things through the climate change forum. We understand that. But what we are doing on the ground work, what we are urged to do is a groundwork, traditional burning. Need to, keep continuing for our people, for the next generation, I suppose. Everybody need to come together, government, indigenous people to start, coming and engaging our people together and working the way and making it possible for this program or this burning issues become a reality.
Today, Dean is recognized as one of those who knew how to protect the Aboriginal populations of the North from the risk of great fires. In Aboriginal culture, fire is alive. You have to be able to converse with this adversary if you want to avoid chaos. But how do you tame a monster? All scientists agree on one thing: multiplying fire trucks will not change anything. It is by combining scientific and ancestral knowledge that we can prevent the appearance of these extraordinary phenomena. August 2021 holds the sad record for the highest rate of CO2 emissions from forest fires ever recorded. The exceptional could well become the norm. The planet has all the means to confront these fires, provided that it recognizes that the fight is now universal.